Here's problem 918. Two blocks with masses 2 kilograms and 3 kilograms are placed on a horizontal frictionless surface. A light spring is placed in a horizontal position between the blocks. The blocks are pushed together, compressing the spring, and then released from rest. After contact with the spring ends, the 3 kilogram block mass has a speed of 2 meters per second. How much potential energy was stored in the spring when the blocks were released? Okay, so let's envision what we have here. We have these two blocks. It's called mass 1, 2 kilograms. And we have a spring put between them. Mass 2 is 3 kilograms. The spring has been compressed and then released. So this is the way things look like initially. And then after they're released, mass 1, with possibly the spring attached, will be moving to the left here with some final velocity, v1 final, which we don't know. And mass 2 will be moving to the right with some final velocity. And we're told that that has a final speed of 2 meters per second. So initially both of these had zero velocity. So v1 initial was 0, v2 initial was 0. It had stored energy in the spring, and that's what we want to find out what that is. So this is the way things look like finally. Well, we can imagine that all the energy of the stored spring is going to go into the kinetic energy after the spring is released. So if we could find the kinetic energy in the final situation, we would find the potential energy of the spring when it was initially released. And so we can use conservation of momentum to find the final velocities and then calculate the final kinetic energy. So let's use our one equation to rule them all. Mass 1 v1 initial plus mass 2 v2 initial equals mass 1 v1 final plus mass 2 v2 final. In this case, v1 initial is 0 because mass 1 is at rest, and v2 initial is 0. So our initial momentum actually is 0. So we have 0 is equal to mass 1 v1 final plus mass 2 v2 final. We want to find what v1 final is, so we have that mass 1 v1 final is equal to a negative mass 2 v2 final, or v1 final is equal to a negative mass 2 divided by mass 1 v2 final. That's going to be equal to a negative mass 2 is 3 kilograms, mass 1 is 2 kilograms, and v2 final is 2 meters per second, so this would be a negative 3 meters per second. That is the final velocity of mass 1. So far, so good. That would mean that our kinetic energy, our final kinetic energy, which is 1/2 mass 1 v1 final squared plus 1/2 mass 2 v2 final squared, is going to be equal to 1/2 times 2 kilograms. v1 final is a negative 3 squared plus 1/2 times 3 kilograms times 2 squared. 1/2s cancel over here. One of the 1/2s and 2's cancel over there. And so this would be negative 3 squared would be 9 plus 6, or 15 joules. That's our final kinetic energy. But we wanted to find the initial energy of the spring when it was compressed. Well, we know from the one equation to rule them all that the kinetic energy at A plus potential energy at A plus any work done along the way equals kinetic energy at B plus potential energy at B. In this case, the A situation is our initial situation and the B is our final situation. There's no work done along the way, and everything's on a flat plane, so there's no gravitational potential energy. And in the final state, the spring is sprung and will spring no more, so our final potential energy is 0. Our initial kinetic energy was 0 as well, because we were not moving. So we strictly have that the initial potential energy of the spring is equal to the final kinetic energy of the system. Well, that's our kinetic energy at B, and we just determined that that was 15 joules. So that 15 joules is also the energy that we had in the compressed spring at the start. So that is the potential energy stored in the spring when the blocks were released.